Slides, yes. Yes.
PowerPoint?
Yeah, Dr. Hikida, you have 30
Can I start?
minutes. You have 30 minutes, but please use your 25
Okay.
minutes and 5 minutes for the questions. Thank you.
Okay. Okay, thank you very much. So I'm Yasuaki Hikida from YTP, Kyoto University, and I want to talk about rate-time correlation functions in 3D dS3 CFT2 correspondence. This talk is based on collaboration with Tatsuma Nishioka at Osaka University, Tadashi Takayanagi at YTP, and Yusuke Hikida, Tadashi's student, and also Henyu Chen at National Taiwan University, and Shi Chen, his student of Henyu Chen. And this good picture is taken from Outreach Journal published by APS, which review our this first paper. So I like this picture very much because it illustrates the concept of DSCFT correspondence very much. Okay, so sorry, I cannot see the chat box. So if there's any, okay, I can see the chat box now. Okay, so this talk is about DSCFT correspondence. DSCFT correspondence should be very useful to understand quantum gravity on digital space. Maybe, sorry. Sorry, what's happening now? Okay. Sorry, let me continue. So DSCFT correspondence is important to understand quantum gravity on digital space because we all know that ADS-CFT correspondence is quite useful to understand quantum gravity on undigital space. So quantum gravity on digital space is important if you want to understand our early universe, which is approximated by digital space. I'm not used to this. Sorry, I'm not used to this. However, a DSCFT correspondence is not well understood if you compare with ADS-CFT correspondence, because there might be many reasons why, but one reason is that now very few concrete examples are available. One famous example is proposed by Alinos, Hartmann, and Strominger, which is given by duality between higher spin gravity on 4-dimensional digital space and 3-dimensional SPN vector model. And it can be understood as an analytic continuation of so-called Klebanov-Polyakov duality between higher spin gravity on 4-dimensional anti-digital space and 3-dimensional ON vector model. And let me give a brief review of DSCFT correspondence. In the DS space, one important object is given by wave functional of universe, which is given by integrating over all fields and up to this boundary condition. Here we consider so-called Hartle-Hawking wave functional, where universe starts from nothing and connect to digital space. And Another proposal is that this wave functional can be identified with generating function of dual CFT, if there is dual CFT. And this is very close to GKP Witten relation, you know. But there's a crucial difference that this is wave functional, so we cannot. This is not observable. So, for example, if we want to compute a partition function, then we have to consider square root of it and integrate over all boundary field. For example, in the case of Hartree-Hawking wave function, this digital part gives a real contribution here, so this gives only pure phase. So if it disappears, only this Euclidean part remains. So this partition function reduces the computation on the sphere. This factor will be used later. And the aim of this talk is as follows. We first propose a new dS3 correspondence involving three-dimensional higher spin gravity. I mean, duality between higher spin gravity on three-dimensional dotted space and the two-dimensional SUN Westminster model. And we provide evidence by comparing partition function. I mean, compute partition function this side and this side and find agreement. And we also relate this duality to so-called Gaberdiel-Gopakumar duality, which is dS3 higher spin holography. And by utilizing this duality, we compute rate time bulk correlations, as in the title, and we find consistent result with previous one, which was done by Scheid and Tarona. And this is plan of my talk. I already finished the introduction, and then I want to move to the computation of partition function. Then I want to relate our proposal to Gaberdiel-Gopakumar duality, and then I want to relate. I want to compute rate time bulk correlated and then conclude this talk. Okay, so our proposal is as follows. So our proposal is duality between higher spin gravity on three-dimensional dotted space and two-dimensional SUN Westminster model. And in the following, we focus on the simplest case with n equal to. Then this reduced to actually Einstein-Hilbert, Einstein gravity on three-dimensional dotted space. And we want to compute partition function on both sides and find agreement. And this side is actually not difficult to compute, but this side is actually tricky. If you want to, so if the base manifold is a torus, then it can be well defined. But it is now base manifold is now a sphere, and it is somehow tricky to compute partition function on sphere. And we use the Witten method to compute this partition function. But before going to that, let me explain. So here we want to realize right central charge of Westminster model in order to relate a classical limit of higher spin gravity. And I want to start how to realize this right central charge. So this is a Hartree-Hawking wave functional, as we saw before, and dual CFT are living at the far future. In the near far future, Strominger found that Pierce symmetry appears. Conformal symmetry enhances the Pierce symmetry, and the central charge is computed like this. So one important point here is there's factor I here. So central charge is now pure imaginary. So this is quite peculiar because central charge is somehow related to degree of freedom. So this means this CFT has an imaginary degree of freedom. So it is quite strange. But so this is a typical situation in the dS3 correspondence, and this is one reason why a dS3 correspondence is not so well formulated compared to ADS3 correspondence. Anyway, this is the formula, and the LDS is the radius of the charge field, and Gn is a Newton constant. And if we take classical limit, I mean Gn to the limit, then central charge diverges. I mean central charge is given by I times infinity. And now I want to realize this central charge from S2 Westminster model. This is the action of Westminster model. This is kinetic term, and this is so-called Westminster term, topological term. And if we plug S2 element, then this becomes S2 Westminster model. And the central charge is related so-called level. Level appears here, and it is given by here. But one problem here is that now level is assumed to be positive integer, but for positive integer k, central charge cannot be large. The maximum number is 3. Therefore, we have to relax the condition, and we take some analytic continuation on k. So if we relate, if we equate this equal this, then we obtain this equation. Therefore, we take this peculiar limit. So originally this is defined by a positive integer k, but we perform some analytic continuation to this value of k. And now we want to compute CFT partition function. As I said, it is quite non-trivial to compute it, so we use written trick. I do not explain some detail but the derivation, but I provide here only the result. So the partition function is computed in terms of modularized matrix of S2 Westminster model. Modularized matrix is a coefficient when we act S transformation to torus partition function. And so the detail is not important, but the important fact here is that this S matrix is known explicitly. And by using this one, we can obtain partition function. And here we use this limit, as we saw before, and J and L are set to be 0. Here. So this is the prediction from CFT side. And I want to reproduce it from gravity side. This is not so difficult because partition function of gravity side is defined like this. Here I is Einstein-Hilbert action, and if we plug metric of there, then we can evaluate here like this, and this reproduce this one. So in this way, we find much of partition function, computation partition function. And here we take J and L equal 0, but if we use generic J and L, then this corresponds to black hole geometry, and even in that case, we find agreement with two types of computation. This was explained in our paper. Okay, let me proceed to compare Gaberdiel-Gopakumar proposal. So actually, there are two versions of Gaberdiel-Gopakumar duality, and here we want to use not familiar one. I mean, so here duality is between higher spin gravity on three-dimensional anisotropic space and coset model of this type. And the point here is that there is a upper bound for the spin, and this upper bound n is related to this n here. And we focus on the simplest case with n equal to. In this case, this reduced to Einstein gravity on ATS, and 2D cosette model of this law. So this is same as Virasoro minimal model if case positive integer. And here actually we have to add some matters here. And as before, we want to compare central charge of this from this and this side. And from this side, actually, this computation was done by Brown-Fenol. This is very famous result, and it was found that symmetry enhances to Virasoro symmetry, and the central charge is given by this. So previously I present some results by Strominger, but this is just a kind of analytic continuation of this one. And central charge of cosette model is given by this one, and we did equate this and this. Then we obtain this one. This form is very similar to the previous one, and actually there is some reason why this is quite similar to the previous one. And now we review duality for ADS high spin holography. And now I want to relate. Now I want to analytic continue from ADS to DS. This can be formally done by replacing LADS by I times LDS. Then negative cosmological constant becomes positive cosmological constant, basically. Then Einstein gravity on three-dimensional antidotita becomes three-dimensional dotita space with some matter. And for 2D cosette model, central charge becomes actually imaginary. And so previously, so we find this central charge. And if we replace LADS by this value, then we obtain this central charge. So this is a result by Strominger. And now I want to equate this central charge of Virasoro minimal model with this one. Then we obtain this one. This is actually the same as the expression I presented before. So this has a reason, because so here we provide a non-trivial expectation value only for gravity side. I mean, only we consider non-trivial metric. Therefore, we give some expectation value for the graviton part, but for the matter part, we do not do that. So therefore, at the leading order, only gravity part contribute. And in the CFT side, if you take this limit, then this term dominates. So central charges become very large, but the other part are subdominant. Therefore, if you take this limit, then only this part dominates. Therefore, we can relate Einstein gravity and SU2 model. In this way, we can derive our duality from Gaberdiel-Gopakumar proposal. So, by using the rest of the time, I want to explain our computation of spacetime Barclay data by using dS3 correspondence. As I said, wave functional can be computed by a generating function, correlation function. This is a proposal of Mardelson. But there's actually crucial difference between ADS-CFT correspondence and dS-CFT correspondence. In the case of ADS-CFT correspondence, this is a source. So this is some fixed value, at boundary value. But in the dS-CFT correspondence, this is actually dynamical field. So therefore, it is convenient to expand in terms of boundary field. And the late time correlator can be computed as expectation value like this. Here we perform some path integral over boundary field, but the weight is given by scale of wave function. And we can evaluate this at the classical limit, then this becomes this one. And if you want to compute a 3-point function, then you insert a 3-point here, and with this weight, then we obtain this one at the classical limit. So in the case of ADS-CFT correspondence, correspondence between correlation function and the boundary amplitude is quite straightforward, but in the dS3 correspondence, correspondence is quite non-trivial, something like this. But in any case, once we know the correlation function of the CFT, then we can compute bulk correlator by following this formula. But now we want to compute a correlation function as an analytic continuation of correlation function, which is dual to ADS3. And so we perform some analytic continuation. And during the analytic continuation, we have some phases. And this is something we have to take care of. And let us see what's happening here. So this is a metric of ADS, well-known Poincare metric of ADS. And this is Poincare metric for digital space. And this and this are very close to each other. In fact, if we replace this way, so L is replaced by IL, and Z is replaced by IY, then this becomes this one. So by using this replacement, we can map from ADS to DS at the level of metric. And we want to give a map for bulk field. A bulk field can be expanded something like this near the boundary. Near the boundary, I mean, so boundary is located here, and near the boundary, we can expand bulk field something like this. And this power corresponds to conformal weight of conformal dimension of dual operator. And we can do the same thing for digital space. For digital space, we have this time direction, and we expand some near here. And now y equal minus infinity is around here, and y equal 0 corresponds here. So we take this form. And if we relate this one and this one, then we can obtain relation between this one and this one by using this. Yes, and we have phase factor coming from this part. And bulk coupling is given by this. And if we require that this is this becomes this one, then we can see that we need this phase factor. Therefore, if we want to relate a map from map of correlation, if we want to map ADS operator to DS operator, then we need to assign this phase factor. This phase factor is very important, and combining this phase factor and this factor here comes from the scale of this one. So this here and phase factor provides some factor like cosine or sine or something like this. And so by applying our prescription, we succeeded to evaluate correlation function of digital space, and our prescription provides some factor if we compare the same amplitude in the case of ADS. So we can relate ADS amplitude and the digital amplitude with this phase. This kind of relation is not, we are not the first person to obtain this kind of relation. This kind of relation was already known. This was obtained purely from bulk side by using Feynman formulation by this beautiful paper. So this picture is actually taken from the paper. So in this way, we found our result is consistent with previous one. So let me conclude this talk. So we propose a dS3 correspondence between higher spin dS3 gravity and 2D SU investment model. And we provide evidence by comparing Partition function and relate to higher spin holography, Gaberdiel-Gopakumar duality. And we compute a less than bulk correlator by applying this dS3 correspondence. And the results are consistent with those obtained from purely bulk analysis in formulation. One important future problem is that now we so when we compute best minute some quantity in the best minute model, we
thank you very much.
Some analytic continuation from in the
okay,
level.
Thank you very much, Dr.
Level used to be
nice talk.
some positive integer number, but we take some complex number.
Any question?
And the analytic continuation is actually quite
you can raise your hand
and
or write your comments and
quite
questions.
nice, quite rich structure. And now we are preparing a paper. And here actually we are considering only three-dimensional digital space. 2 + 1.
Okay, Dr. Hikida, let me ask you a very quick question. My question is about the renormalization of the UV divergences.
Extend our analysis to higher dimension.
How you overcome this problem
higher spin gravity,
in your approach?
And higher spin gravity is very special one, so it is nice if we can
Dr. Hikida,
achieve correspondence by using string theory. Thank you very much.
Yes, Dr. Hikida, I have a question.
So that's all I wanted to say.
Okay, okay, my.
What's happening here? Yes.
But my question is about the symmetry. But when you introduce a cutoff, it maybe causes the symmetry breaking of the system, Lorentz symmetry of the system.
Can you
so,
no?
Is it any physical problem or?
Yes, I hear that question. So you are asking, you are asking about the UV divergence or IR divergence. I'm not sure what it is, but there's an IR divergence associated in infinite volume digital space and here, and this is related to UV divergence of this dual CFT. This is quite similar to usual ADS CFT.
Okay.
So we need to introduce some cutoff here and take some limit to infinity. So is it what you're asking? So prescription
okay.
is quite
thank you very much.
Yeah,
thank you very much, Dr. Okay, sure. Okay, thank you again. Thank you very much. And